let us start with star delta transformation in lecture 55, and this is the thing we have done for star delta transformation. That is, if you know this R 1, R 2, R 3 in delta fashion at A, B and C, then you can replace R 1, R 2, R 3 by some star connected loads R A, R B, R C, and this R A, R B, R C, if you know the values of R 1, R 2, R 3, then R A, R B and R C can be found out. Okay. Also, now I want to find out the reverse formula, that is, if R A, R B, R C are known, then what should be R 1, R 2 and R 3. So, to find this out, what we do here is this one, that is in lecture 55, you see if you take this ratio R A by R B, which at the three values is known, it comes to that. Now, what we will be doing is we will express R 2 and R 1. Let me write these ratios very clearly, that is, we have got these ratios R C is equal to R 3 by R 2 into R A. Therefore, and another important ratio is this one. Therefore, for example, from this I express R 3 in terms of R A by R B into R 1. I can write it like this. Similarly, I would express R 2 in terms of R 1. R 2 by R 1 is this. So, it will be R B by R C into R 1. R 3 is equal to R B by R A. Thank you. R B by R A. So, these two I have expressed R 3 and R 2 in terms of R 1. Then I go to say this equation, which has already been established, and I will say that R A is equal to, from this, R 1 into R 2. So, R 1, I will express everything in terms of R 1 here, R 2 and R 3 in terms of R 1. So, that on the right hand side only R 1 and R A, R B, R C will be there. So, I will be able to express R 1 in terms of R A, R B, R C. So, R 1, and for R 2 I will write R B by R C into R 1, R B by R C into R 1. This I will write, divided by, this is R 1 is there, plus for R 2 I will write R B by R C, R B by R C into R 1. Plus R 3, but for R 3 I will write R B by R A, R B by R A into R 1, like this. This I can write. Then you see that there are R 1 square on the top and one R 1 will come out. So, this will be equal to, if I clean this up. So, this will be equal to, R 1 into R B by R C. One R 1 will go and it will be 1 plus R B by R C plus R B by R A. This will be the thing, and that I am telling it is equal to R A. Therefore, if I take all these things to the right hand side, keeping R 1 on the left hand side, I will get R 1 is equal to R C into R A by R B and whole into 1 plus R B by R C plus R B by R A. That is over, but you push it this inside, then what you will be getting? You will be getting R C R A first term by R B plus 1 plus this R B and R C will cancel out, you will get R A here, and the third term will be R B and R A will cancel out plus R C, and you are done. So R 1, the value of R 1 will be equal to R A plus R C plus product of these two divided by the third one. Therefore, paste ki ache ekhono? It is still there. So, finally, this is the thing. Therefore, if the equivalence between these two circuits, we have already seen for delta to star transformation, delta to star, first we derive that is this, that R A is equal to R 1 R 2 divided by R 1 plus R 2 plus R 3. R B was equal to, R B is this resistance, R 2 R 3 divided by R 1 plus R 2 plus R 3. They could be also impedances, do not worry. R C is equal to R 3 R 1 divided by R 1 plus R 2 plus R 3. So, if the delta values of resistances are given, equivalent star can be made at those 3 points A, B, C. And for star to delta, transformation, that is, you know the value of R A, R B, R C, then what should be this R 1? This is here the R 1 should come. So, it is easy to remember R 1 will be equal to the sum of the adjacent resistance, that is R A plus R C plus R A R C divided by R B, product of these two divided by the third one. Similarly, for this I have done, and similarly for the other I will be in the similar way, I will be able to do that. R 2, that is this resistance, that is R 2 will be how much? R A plus R B, adjacent resistances, sum of them, R B plus R A divided by R B R A by R C, and finally R 3 will be R 3 is this one. So, it will be R B plus R C, R B plus R C plus R B R C by R A. So, when it will be necessary, for example, if you have a circuit like this, suppose I say that you have a 3 resistance. Now, I am coming to a problem, what I am asking to tell you, and there are 3 resistances here connected. Just a simple example. Suppose these values are known, 4 ohm, 6 ohm, 10 ohm. This is how 6 resistances are connected, and this is a 1 ohm, 5 ohm and 7 ohm. It is there. Now, you have a circuit like this, another resistance here 10 ohm. Suppose I ask you what is the equivalent impedance looking from the points A and B, which you are supposed to do after replacing the sources in any network to find out R Thevenin's or Z Thevenin's. Now, here the knowledge of simple series parallel equivalent resistance formula will not work, because the resistance value R A B will be 10 plus the equivalent resistance of this network between these 2 points, and that is very difficult to find out, because I do not know this 1 ohm whether it is in series with 6 ohm or in parallel. No, I am not sure. Similarly, 4 ohm. Then what I will be doing is this, I will be changing this. See, these 3 points are fixed. This is A, this is B, this is C. Question is, what is R equivalent? So, what I will do? I will replace this delta connected resistances 4 ohm, 6 ohm and 10 ohm in points A and B, C by a equivalent star I can do, or I can change this star to equivalent delta. So, change star connected 1 ohm, 5 ohm and 7 ohm in equivalent delta. So, how it will look like? So, there were this 4 ohm, 6 ohm and this 10 ohm is there, this I am not disturbing, 10 ohm is there. Here was some additional resistances 10 ohm connected here. So, let this remain 4 ohm, 6 ohm and 10 ohm. Now, this 1 7, this I will replace it by the equivalent delta here. Another resistance will come there, another resistance will come there, another resistance will come there, and then I will replace forget about this star connected 1 ohm, 7 ohm and 5 ohm. So, what will be this additional resistance across ABC? There will be this resistance, and what will be the value of this? It will be 1 plus 7 start to delta, 1 plus 7 plus 7 by 5, is not? R A this plus this into this divided by the third one 5 ohm. How much it is? Some value will come. Is it coming 9.4? So, let us put it. Similarly, this I will replace by a resistance here. What will be this value? It will be 7 plus 5, let me write 7 plus 5 plus 7 into 5 divided by 1, 47, whatever it is. And finally, here there will be another resistance connected between these 2 points, and this resistance value will be this one. If I write it here, it will be 1 plus 5, so much ohm, 1 ohm plus 5 ohm plus 5 by 7, 6.7 ohm or so. Now, I will not carry on with this calculation, I just told you this is this portion. Then I have been asked to calculate the equivalent resistance of this. Then you see this 6 ohm and this red resistance are in parallel. Formula can be applied. These two are in parallel, I can easily calculate these two are in parallel. Then this and this will mean series, and this equivalent resistance can be easily calculated, which will be 10 plus this equivalent resistance between these 2 points. It is just to tell you that in some situations, when we cannot make out whether the resistances or impedances are really in series or in parallel, the star delta transformation or delta star transformations are very useful. That is how it has been pointed out. I hope you have understood it. See problems to find out equivalent impedance when the resistances are connected in an awkward fashion. Achha, today now what I am planning to do is to start another interesting theorem, and that is called the intelligence theorem. Okay? So, let us start that, at least the idea, intelligence theorem. Intelligence theorem is a very interesting theorem. It is only applicable, but before we start the real intelligence theorem, you please try to recall that in any network there may be sources, there may be several impedances connected like this. Suppose you have a network like this, then in this network there will be several elements connected, and you can have another elements connected here in between these two. Suppose you are considering this network. These elements could be also source, this is another element, another source here. But whatever it is, in this network, suppose I say the voltage across each element, I will call it some values, say V 1, voltage across this element V 2, understood? This is suppose V 3, what not, V 3 and so on, and V 4, V 5, V 6 and V 7. And also arbitrarily, if I assume the currents I 1, I 2, I 3 and say I 4, say I 6, I 7, I 5. This way I have done it. This of course, you must understand in this diagram this I 3 and I 1 are same. So, let us consider only one element in this branch. They can be combined, so there is nothing like this one. But what I am trying to tell, given a network, I will be able to calculate the voltage across each element. That element could be an impedance as well as an source, and also I am able to calculate the voltage across each element. Now, in a network, if you calculate the product of voltage and current and sum them up for all the elements, it will come out to be 0. Okay? That is precisely whatever I am trying to tell. For example, I say that what is the power delivered by this element? This will be V 1 I 1, this element after I have assumed. So, delivered, I was writing like that, delivered, and here I will write absorbed. And once you have assigned the voltage polarities and the current, do not play with that. So, this is the, it is delivering power. What about element doing? Element 2 is absorbing power, because current is entering through plus. So, it will be V 2 into I 2. Element 2, it is absorbing power. Element 3, of course, nothing. Element 3, here it is element 4, it is also absorbing power, V 4 I 4. And element 5 is also absorbing power. So, power absorbed is given by V 5 into I 5. And element 6 is also absorbing power, V 6 I 6. Element 7 also absorbing power, V 7 I 7, is not? So, how many elements are there? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Another is left out. V 1 I 1 is another element. Therefore, I will say that in this network, this equation is correct. V 1 I 1 delivered is equal to V 2 I 2. If I miss the terms, you please tell me, plus V 4 I 4 plus V 5 I 5 plus V 6 I 6 plus V 7 I 7. This we have learned, in any network it has to happen. It has to happen at all times, even if they are time varying. So, volt ampere supplied, power supplied instantaneous must be equal to sum of all the powers of other elements. Now, this equation also I could write it like this, that V 1 minus I 1, I will bring this term to right, plus V 2 I 2 plus V 4 I 4 plus V 5 I 5 plus V 6 I 6 plus V 7 I 7. In that case, I will tell that I have written all the elements as if they are absorbing power. Total power absorbed by this network V 1, how much power it is absorbing? V 1 and minus I 1 is entering through plus. So, V 1 minus I 1 is the power absorbed by this source. V 2 I 2, and why negative sign? Because we know to absorb power through the plus, current must enter. But since I have assigned current along the leaving the positive terminal, therefore, I have every right to say that minus I 1 is going towards positive and calculate this, and then you tell that power absorbed by V 1, which will come out to be negative. That means, it is really delivering power, power absorbed by V 1, and these are of course all power absorbed. So, this way I can write. Therefore, henceforth what I will do in a networks, I will assign the currents and voltages and always calculate power absorbed by different elements. I am sure that some of the terms will become negative, let it will become, but mathematically that is also correct. So, remember that in any network, this is one of the conventions better follow, instead of separately keeping track of power absorbed, power delivered, always try to make a habit, okay, how much power is absorbed by each of the elements. In that sense, I will write it, and that sum has to become equal to 0. From this I get. One could also say that I will always calculate power delivered by the network. So, power absorbed, same equation could be written based on power delivered by each element with that concept. each element as if delivered powers. Then I will write V 1 I 1 it is really delivering, but V 2 I 2 how much it is delivering? V 2 minus I 2 plus V 2 into, then I should not write plus I 2, because in language I am written delivering V 2 minus I 2 plus V 4 minus I 4 plus V 5 minus I 5 plus V 6 minus I 6 plus V 7 minus I 7, and this will be 0. In fact, this is the same equation I have written, I have just changed the side of each terms to the right. So, you will be writing the correct equations, no matter whether you are calculating it considering all the elements to be absorbing power or delivering power. So, I will assume all the elements are absorbing power. Now, this is not Telligence theorem, this is known in a circuit, and with numbers I can very neatly write down and clearly write down which are the elements which are actually absorbing power, which are the elements which are delivering power. We have discussed it in length. Now, what the Telligence theorem tells us, that suppose you have a network. Now, let me be a bit methodical in telling about the Telligence theorem. Suppose consider a network like this. And here also another element is there, and there is also an element connected here. In general I am telling. So, it is a network and these boxes are elements, some of them could be sources as well, I do not mind. So, source I am not drawing separately. Now, what I will tell, that I will name the elements. For example, this element I will call element 1. Voltage across it I will write V 1 and I 1, quite arbitrarily. This is my prerogative. In solving network, you assume polarity and current in whichever fashion you like, but once you assign that, write down correct KVL and KCL. Okay, so let this be element 1, let this be element 2, whose voltage at any time is assumed to be with this polarity and current is assumed to be I 2. Let this be element 3, V 3, this is I 3. Let this be element 4, voltage across it is V 4 and current is suppose I 4 and in this direction, and then this is suppose element 5 V 5 and current is flowing I 5, and this is the voltage across the element with this polarity V 6 and current is I 6. I can do that. Is not? How many nodes are there in the circuit? 1, 2, 3 and 4, and let me name the nodes as A, B, C, and let this node be called O. Say reference node, with respect to that I will calculate all the voltages. So, have you understood this thing? This is very important. A general network I have taken, and in each branch there may be two series elements, I have combined them and I am calling one element is connected. One of these boxes must have been the source, otherwise how current will survive. Okay. So, this is a network, and this is the topology of the network. Now, I draw a similar network structurally similar network like this. I have drawn another network. Now, this network geometrically or topologically they are identical, okay, same type, 3 loops, 4 nodes and so on. But only thing, these elements could be totally different from these elements. Another network, for example, here there was a resistance, here maybe there is an inductance, here there was a source is here. So, these two networks are totally different networks, except for the fact that their topologies are identical. Topology of the networks of these two networks are identical. Got the point? And this network is since separate, I will name their thing with dashed element, A dashed, this node is B dashed, this node is C dashed, and this node I will call O dashed, like that I can write. Similarly, the voltage and current assumed across each elements in this network, I will follow the same rule as I have done here. For example, I will say this is the voltage across the element in this dashed network, and I will say the voltage across it is V 2 dashed and the current is I 2 dashed. For this element, I will say the voltage across this network is V 1 dashed and current is I 1 dashed. This was plus minus V 5, this is the voltage across this element, current is I 5 dashed, this is V 5 dashed. This is also plus minus V 6 dashed, and the current in the same direction I will show I 6 dashed, and this is plus minus V 4 dashed and the current is I 4 dashed, and plus minus this is V 3 dashed and the current is I 3 dashed. So, these two networks have otherwise totally different network. Elements may be different, only they are structurally same topology and with different elements, but the voltage across each element, their polarities I have assumed in the same way as I have done here. Obviously, the currents I 1 dashed, I 2 dashed, I 3 dashed, I 4 dashed will be decided by what are the sources present here, what are the impedances, they will decide the current, loop equations, this that you solve, and that is supposed to be different from I 1, I 2, I 3, I 4, I 5. Similar is the case with the voltage across each element, that is V 1, V 2, V 3, V 4, V 5. They are naturally expected to be different from V 1 dashed, V 2 dashed, V 3 dashed, V 4 dashed and so on, is not. So, Telegen's theorem talks about two networks, two or more networks which have got same topology, and we will continue with this in this next lecture. Thank you.